we are going to be looking at the game of life problem and build a solution in JavaScript while also computing the time complexity and space complexity of the solution that we will be building. Before jumping into the solution aspect, let us first try to understand the problem statement. We are dealing here with a progeny of live cells, and a live cell is represented by a 1 in the m by n input matrix that we are going to be receiving as an input, and 0 is going to be representing a dead cell. We have to find what is going to be the next state of a progeny of cells that we have based on a certain set of rules. First rule says that we have to make these updates simultaneously to all the cells in the matrix that we have received, and then along with this we have to work with two rules that we are given. First rule will say that if the neighbors that are associated with a cell, now what are these neighbors that are associated with a cell? Let's say we start with this cell here. It has 8 neighbors associated with it. 1, 2, 3, 4, 5, 6, 7, 8. These are the neighbors of the cell which are going to affect its life in its next state that we are trying to find. And how that is affected is, if you have exactly 2 or 3 neighbors around you that are alive, then you stay alive in the next state of your progeny. But if the number of live cells around you is less than 2, then the current cell is just going to die. And if the count of live cell neighbors around you is more than 3, then it's just going to die by overpopulation. So you either die by underpopulation or overpopulation. And if you are already dead in the current state that the matrix is at, if you have exactly 3 neighbors that are alive, then you will be brought back to life by reproduction. And we have to make sure that these changes are simultaneous, because let's say I have a 0 here. Now this 0 is affected by its 3 neighbors. If I, while going through my matrix and trying to change the values to reach the next state, update the state of this one to 1 here, then the logic of applying the rules will change, because originally the state was that this neighbor was dead and now you made the neighbor alive, and then when counting the neighbors of this current cell, instead of 1 alive that is currently there, it will have counted 2 alive, which is not what we want. That's why we have to make sure we consider the original state of the cells that we have received while making this determination that in the next generation, the next state, whether the cell is going to live or not. And to do this, we can take 2 approaches. The first approach is that we can try to make a copy of the original state and then try to reach the next state, so that we make sure that when we consider the values and try to move from start, that is the top left, to the bottom right, we are considering the correct values of the original state, and the rules are not being applied in such a way that the data gets corrupted, because we have to make sure we consider the original state itself and not the change state that we have determined by applying the rules as we move along through a matrix interpretation that we have with us. And to do that, either we said we will be using a copy, or another way is that we can try to introduce a few new states into a mechanism and make these changes in place within the matrix that we have received. And how we can try to do that is think of the deaths in another perspective. Like, if you have died by underpopulation, instead of changing immediately the value to 0, we will introduce a intermediate state and say that it's going to be -1 if you have died by underpopulation, and it's going to be -1 if you have died by overpopulation. And then this intermediate state will finally be changed again to 0 when we again go from start to end of a matrix. And if you have been brought back to life by your neighbors, instead of directly changing it to this live state of 1, we will introduce another state called as 2, which will represent that you have been brought back to life. This way, we will be able to say whenever we are trying to do checks for the neighbors whether the original state was that it was dead or it was alive, because if it is -1, that will mean that you were originally alive, and if it is 2, that means you were originally dead, and if it is staying 0, that means it's already dead, it doesn't change, and if it is 1, then that means it is alive. And with this in mind, let's try to approach the solution. So we'll keep an intermediate state, and then we will try to reach a final state that we want to reach here. So this will be a intermediate state that we keep a track of to reach the final state that we are trying to have with us. We'll start with the top left here. This one is already dead here, and we will now see what do we do with dead cells. So the first check is for live cells, that is, for it to stay alive, you have to have these 2 or 3 neighbors that are alive. And if it is already dead, then you go and check whether you have exactly 3 neighbors that are alive. I see one neighbor that is alive, another which is dead, another which is also dead. So 1 is not enough to bring it back to life. I will just keep it as 0 itself. Then I move on to the next one, which is my 1. 1 is having 0, 0, 0, 1, 0. So just one neighbor that is alive. If you just have one neighbor that is alive, then the rule applies that it is underpopulation and it unfortunately dies. And now the part of this intermediate state comes into picture. So now we will say that instead of updating the value to 0, we will update the value to -1, because then we will know when we are trying to consider this for its neighbors, because this here can be a neighbor to this, this also can be a neighbor, this also can be a neighbor, this also can be a neighbor. So for this, I don't want to affect by my updated value. That's why I'm keeping this intermediate states. And then I move on to the next one. So I have a 0 here, so it's dead. I will try to apply this second rule that I have here. Do you have 3 number of live cells neighbors around you? You have one neighbor that is alive, you have another neighbor that is alive in the original state, so you stay dead, because you need exactly 3 neighbors that are alive to reach a state of rebirth. Then I go to this one. This one has 0, 0, 1, 1, 1. So 1 plus 1 plus 1, it has 3 live neighbors around it, and when you have exactly 3 live neighbors around you, you will be brought back to life. Life is 1, but we said we are introducing our intermediate state here, which is going to be 2. So instead of 1, I will temporarily make it a 2. And then I move forward. I move on to this one. I see 1, 2, 3, 4, 5 neighbors that are alive. But we said we have to have exactly 3 number of neighbors to make it alive. So it stays at 0. Then I move on to the next one. This one has 0, 1, 2 and 3. So 1, 2 and 3 falls in the criteria of having at least 2 or 3 neighbors that are alive. So you will stay alive as you were. So it stays as 1 itself. Then I move forward to the next one, which is here. I will see how many live neighbors do I have. So this is 0, 0, 1, 0, 0. So it just has one live neighbor. That means it's going to die by underpopulation. In that case, I will update the value to -1 now. Then I move on to the next one. This one has 1, 2 and 3 neighbors that are alive. So it still satisfies the criteria of 2 or 3 live neighbors. It will stay alive as it is. Moving on to the next one, we have 1 here. It has 1, 2 neighbors that are alive, but you said you need 2 or 3. So it still satisfies the criteria that we have set. So it stays alive. Then I move on to the next one, which is a 0. Can this be brought back to life? I have 1, 2. I need exactly 3 neighbors that are alive. So it is not satisfying the criteria. It's going to stay dead. Moving on to the next one. This one has 1, 2, 3. Exactly 3 numbers of neighbors that are alive. I will bring it back to life, but I will represent it as a 2 now. Moving on to the next one, this is having 1, 2. 2 is not enough to be reborn, so it stays as 0. Then what I will do is I will iterate through this intermediate state that I have created and say that if you have any value which is less than 0, then it's going to be 0 itself. So it will be 0, this is -1, which is 0, 0, and if you have anything greater than 1, then it's going to be this representation as 1 itself. So I will just say 1, 0, 1, then -1 becomes 0, 1 stays as 1, 0. If this is 2 greater than 0, then it just becomes 1 and this becomes 0. And this is the final output that we are trying to reach here. And that's pretty much in terms of the approach that we are following. Either we could have used a copy to try to reach this state by doing checks, or we use this intermediate state here that will be doing this in place manipulation and try to reach the final state that we're having. And that's pretty much it in terms of the logic aspect of it that we have. Now let's jump into the solution aspect of what we have covered so far. We said we want to go through the neighbors of a specific cell in its relative position. So let's say I start at this position, I want to go on the left side and I want to go on the right side. To do that, I will use a neighbors array, and the current position is going to be represented by a 0. So let's say this position is the 0th position. To move on the right side, I will just add 1 in my array to iterate through, and to go on the left side, I will just add a -1 to represent the relative position of the neighbors that we have. And then I want to have a count of the rows that are going to exist. So I will just say rows count is going to be board.length itself that we have, and the columns is going to be, take any board, let's pick the first row of the board, and for this board just pick the length of my first row. That is going to give you the column count that is going to exist in the matrix that we receive. Then we have said we are going to build an intermediate state for us. So intermediate state that is going to be there is going to be built by iterating through the matrix that we have, which can be represented by something like this. We will just start with row as 0. Row is going to be less than the row's length that you have. Keep on iterating, then go through the columns that you have in a nested loop. I will say call is equal to 0, call is less than the column's length that you have, call plus plus plus, and then you try to build this intermediate state here. After you have built the intermediate state, I will then build the final state that I'm looking for. And building the final state will just make sure that if the value is greater than 0, which is going to be represented as either 1 or 2, then you consider it as a 1, otherwise it stays 0. So if the board has a value of row and column that is greater than 0, in that case the final value of that specific cell is going to be 1 itself, because the intermediate can either be for a live cell a 2 or the live cell value itself, which is 1. In that case you just update it as 1. Otherwise, for a dead case, the intermediate can be either -1 or 0, and to represent that we can just make this 0 and that case gets handled. Now comes the part of building this intermediate state. That is the critical aspect which we are looking at. Now to build this intermediate state, we said we want the live count of our neighbors. So I will say live neighbor count is going to be initialized to 0. I will find this neighbor count, and then once I have this neighbor count, I will try to apply the two rules that we have here, the rules here and the rules here. And these rules say that if the current value is live, so that gets represented by board of row and column having a value of 1, and the neighbor population is less than 2 or greater than 3, then you're going to consider that in the next state the current cell is dead. And that will just be represented by something like this. I will say if the live count is less than 2, and another check that we do is for the live count to be greater than 3. If this criteria is being satisfied, that means in the next iteration the cell is going to be dead, and the intermediate representation for that is going to be just saying that instead of updating the value to 0, update the value to -1, because we said if you die by overpopulation or underpopulation, you will update an intermediate value state of -1 instead. Then we have the second rule that says that if the cell is already dead, the cell representation value of board of row and column is saying if it is dead being 0, and the live count that you have with you is exactly 3 for your neighbors. In that case, we said that you will be brought back to life, and that representation is just going to be a value of 2, a higher value than 1 that will represent the state that is going to be brought back to life by its 3 neighbors. And next part is that we want to find out what is the live neighbor count. If I start, let's say, with this specific input cell, I have to go in a 3 by 3 matrix fashion, because it's going to then have 1 2 3 4 5 6 7 8 neighbors, and except this I have to cover all the neighbors to see if I can add that neighbor to my live count. And to do that, what I will just do is iterate in a nested loop. I will say I is equal to 0, I is less than 3, I plus plus, and I will use another for loop here. I will start with j, j is less than 3, j plus plus, and then here I will say if I is equal to 1 and j is also equal to 1, just continue. Otherwise, try to take into consideration. What this line will basically mean is that when you are here in this matrix, at this position, the I value is 1 and the j value is 1. You don't want to consider the cell itself, because you want to consider its neighbors when you're trying to take the count. That's why we just skip the iteration when you reach the current cell position, as we are going to consider this neighbors array that we have and go on the left side and on the right side. And to do that, I will just say the neighbor row is going to be the current row that you have plus whether you want to go on the right side or the left side. Now, if you want to go on the left side, I will just go on the left side. That can be just represented by this current position in my row that I have. So I will go on the 0th position here, which is on the left side of my current value, which is -1. So I will start from this position, then I will go through this entire row, then I will go to my current row, and then I will go to my next row, which is 1. So that is represented by this one. I just have to traverse through these 3 rows and skip one value. And similarly, the neighbor column is going to be represented by the j value that we have. So for the neighbor column that you have with you, what we are going to just do is consider the neighbor value itself. Similarly, for the neighbor value, what we are just going to do is consider the neighbor column value itself. So we'll just say neighbor column is the current column that you have plus neighbors of j that you have, which is the nested loop of yours. As you go through each column, starting from this column, and this column. And then once you find these neighbors, we have to make sure the values that we have are falling within the bounds, because we don't want to go outside the bounds of a matrix. So to do that, I will just say neighbor count has to be less than the row's length, and neighbor count has to be greater than or equal to 0. And I have to also make sure that the same checks are applied for my column count also. So I will say in the case of my neighbor column, it also has to be less than my column's length, and the neighbor column has to be also greater than or equal to 0. And then comes the critical aspect here of this intermediate state. We said we can consider a cell alive by having a value of 1, which is its original state, or its current state being dead by underpopulation or overpopulation, which is represented by -1. So I can safely say that if the current value that I have as I'm going through my iterations is 1 or -1, that means it was originally alive and it still is, or it has died. And that can be represented by saying math.absolute of this board that you have for your neighbor column and row value that you have with you, which is represented by something like this value equal to 1, and then I can say that the cell originally was alive for sure. And if that is the case, then I'm just going to increment my live neighbor count, because the aim here is to first find the live neighbor count and just keep on incrementing to reach the solution. Make sure that the representation for column is correct, and we will try to reach a solution here. So first aspect here that is involved is we build the intermediate state and then we build the final state. To build the intermediate state, we first find the live neighbor count. First we go through the neighbors while skipping the current cell that you have, and the neighbor position is found from this array that we have of us. Try to find the final neighbor count that you have with us, and with this count in mind, then we just apply the rules that we have with us. So this part is the applying rules part associated with it, and then you just reach the final state. And that's pretty much it in terms of implementation that we have. In terms of the time complexity that is going to be involved here, it is going to be big O of m into n, because we are going to traverse all the rows and columns 2 times. That's why it's going to be big O of n. And in terms of the space complexity that is going to involve here, it is going to be big O of 1, because we are not using any additional space here. Only thing we are doing is creating this intermediate state of having additional -1 and 2 values, rather than the original problem that gave us just zeros and ones, and then we build the final state from those values. And that's pretty much it in terms of implementation that we are trying to reach here. Thank you for watching. Please like and subscribe.